Hello, in this video I want to look at my new design for the US2000B to 2000C CAN adapter and how I built an automated tester for it that will work not just for this project but for lots of other projects too. Let's take a look. So in an earlier video I prepared an adapter for some Pylontech batteries. So this adapted them from a US2000B cable so that would fit a US2000C battery, because Pylontech in their wisdom changed the interface between the two models. I made those using this, which is a RJ45 socket, and a cable comes in and we split it out and we push it in using an IDC adapter tool, and we can assemble it, and then we can put a normal RJ45 plug on the other end of a bit of cable that we've carefully stripped. And all being well, provided that we join up all the right wires to the right places and things like that, we end up with an adapter that works. And then to test it, I can kind of put this down and literally use a continuity meter to test between the different pins. So that's all right for a small run of sort of 5 or 6. Above that it gets very, very tedious, and it's also quite error prone, and manufacturing it itself is error prone in so much as it's very easy to end up, particularly on this end, because we're only using 3 of the 8 wires, it's very easy to end up with them in the wrong position. So what I said at the time was, what I should do really is manufacture a PCB. And here is said PCB. So this PCB is very simple. It has the cable mapping on it to map, I think it's between pins 6 and 2, which is where the ground changes position, and pins 4 and 5, which I think are the data, if I remember correctly. So this is specifically made so that we can literally take an RJ45 socket and plug it in and just quickly solder the back. And in actual fact, you assemble them like this, and they literally clip in. And these are actually clipped, they are not soldered yet. So they clip in and firmly hold themselves in place, ready to be soldered. So that makes it really easy and completely removes the ability to make a mistake at that point. Now, having got that, I then of course need a box to put it in. So I ordered these from JLC PCB, so I made these up on my CAD system and ordered them, and they are designed specifically so that these drop in an exact fit, and they have a fixing hole in the centre. Wiggle this around a little bit as it goes in, because there's a lip on these that engages with the box, and we put the lid on, we insert one of these screws, screw it down, and we apply a label. And all we've got to do really is put this together, make sure we put it together the right way, because written on here is US2000C, US2000B. So I just need to make sure that the label aligns with that. Now, the next thing, of course, is I do need to test it. And I do also need to provide a length of cable with it, like this. So these are pre-made. Because, of course, we've got one cable coming from the inverter to the battery, and this has to go in the middle. So that now goes into one end of this, and I need another little cable to go into the battery. So that's fine. That's easy enough to do. When should I test this? So an obvious time to test it is when it's assembled like this. But I'm not going to do that, and the reason is that if we think about testing, I need to deliver a working product to the person who's paying for it. So I can certainly test them like that, and that will do a lot of good. But, and in many ways, if these were coming off the production line, you would test at this point, because you wouldn't want to move faulty items onto the next stage of production. But yeah, this is just a small batch. I'm going to make 10 for the moment. I've got stuff to make 25. And so, for example, I can actually see on here, this pin is actually broken. I can actually see that. One of the pins is bent back. It's not actually a pin that engages with anything, so it wouldn't have made the slightest bit of difference, but I will just straighten that up and refit that. So yeah, so there are faults, but despite the fact this is designed to kind of go together faultlessly, all that has to happen is a pin can be bent during transit, and then it doesn't fit properly. Push it in, and yeah, those are all the pins all the way through now. So yeah, so testing at this point has some value, but if we look at the case, so this drops into the case. Now it can fit either way. And then the lid goes on, at which point it becomes completely symmetrical and impossible to see which side is which. So if I were doing another run of this, having another run manufactured, I would actually make a little change to this. So I'd do two things. You can kind of see, I think, let me just zoom in a bit. So I think you can kind of see in here that there's a hole in the middle marked M3. I'm actually using a 3.5mm screw rather than a 3. I've made the hole a little bit wider. And in the bottom you can see that there's a receptacle to take the end of the screw, and you can see there's some standoffs here, and that's so that I don't have to trim off the bottom of the wires, and all that's worked really, really well. But if I were to do this again, I would do two changes. One is I would make some sort of notch to make this board not symmetrical anymore, so you can't fit it both ways. And I would also make that hole bigger and make that thingy there the positive piece that comes up. So it actually goes through the board and still has a little step on the bottom for the board to sit on. When I assemble this, this surface here touches the top of the board and locks it in place. But it would be better if the bottom were long and the top were not countersunk but counterbored a few millimeters, so that any type of screw head could fit in there, because this I have to fit a specific screw which is a blunt-ended, self-tapping, countersunk, flat-topped posi drive. And I've only found one supplier, which isn't exactly great. It's 25mm long. So with some changes I could make it take, say, a 12mm, which is a really easily available countersunk screw, and I could remove the constraint on having to have a countersunk and have, you know, pan head or whatever's available. The other thing that I would do is perhaps actually make this box so it had a little curve out and maybe a curve in on this end, so that again the actual box is sided, so you cannot assemble it and not know which way round your board is. Now, the fact that this can be assembled the wrong way round means that really what I should do is assemble these. So US2000 is on the right hand side. Pop the lid on, pop the screw in, pop the label on the right way round, and then test it fully assembled, because I've only got to get it in the box the wrong way round or put the label on the wrong way round and things like that, and it actually won't work when it arrives. I mean, it will work, but it kind of won't make any sense to the person who receives it. So I need to test all of that. Now, testing through connections is relatively easy. I could just use a bit of 7/4 logic and I could make it pulse onto each connection one in turn and just see that the corresponding pins light up. I could do that all sorts of ways, using a bit of logic, using an EEPROM even, just to switch through all of the possible combinations. And if this were 8 pins all fully connected, that would also simultaneously test for short circuits, but this isn't 8 pins, it's only 3 pins. So I need to test for short circuits on all the unconnected pins as well. That means I need to apply an input signal in this end and read the values on this end. It also means I need to input a signal on this end and read to make sure that nothing is short circuited on this end. And then I need to do the same on this end. So that's a bit more complicated. So I decided I would use one of these. So this is a PSOC, so Programmable System on Chip, and it's a bunch of analog and digital components all together. And I can make it easily, I can load some software on here which will enable me to control this using Skippy commands. So by using that I can have my PC send commands to this, and my intention then is to use that Skippy to drive some digital ports, put various values on it, read the values back, and so on. So, but you know, this is kind of a bit over the top for that. So I thought, well, in that case, what I'll do is I'll make a more general purpose test unit that I can use for testing all sorts of stuff. And I'll make my software a little bit more complicated so it's easy to write test software for new things as and when I make them. So more on the software later. I'll show you how I structured that. In terms of the Scipion here, we've got a UART built in, which communicates through this adapter here. So this piece here is actually a serial debug section. So it's not just a serial port, it actually provides live debugging of this. So we can actually run this up in software on the computer, and we can single step our code, and we can look at registers and all sorts of stuff, the values in those, as we single step our code. And we can set breakpoints, and we can do all sorts of stuff with the hardware actually running the code, and that's absolutely great. However, when we're not using it like that, this turns into a USB to serial converter, which is ideal. So I can then connect that to some pre-programmed Skippy parsers, and then what I can do with that is, for my, let's say, my parallel port, which I'm going to use for output or input, so it's bi-directional, I can actually just create some API points where, so for a Skippy command, or let's say read value, I can create a read value command that will read the value on the port, send it back through here, code it up, parse it up, and shove it back through the serial port to the PC. So as much as possible of that I can do using some ready-made Skippy software. To make it multifunctional, what I decided to do was to utilize a few of the things on the PSOC. And when I come to the programming, I'll show you the programming environment, and you can see just how many things you can actually fit in here. So this tiny little bit on the right hand side is in fact the 2 ports. So 8 pins going out, 8 pins going in, except these are both bi-directional. So you can program these in all sorts of ways. These basically have got pull down resistors, which pulls them down to ground. And then I can assert a +1 positive, which will put it up to 5 volts, which has got a transistor. So if I output a 0, then actually I'm just turning off that transistor and pulling this down to ground through a resistor. So then I can actually put an input to it, and I can read the value being input. So I can use these bi-directionally with no change to the configuration. Now I can change the configuration in firmware on the fly at runtime, should I wish to do so. So if I want to drive strongly high and low, then I can make it do that instead of having pull downs, for example. Or I can make it pull up, if that's the way I wanted to use it. I can also connect interrupts to all these pins and all that sort of stuff, and I can change that on the fly in my software. So that's brilliant. What else have I decided to put in there? Well, not surprisingly, I decided to put an analog to digital converter in. Now, at the moment, this is configured as 16-bit single shot. So I can send a command through Skippy saying, read the analog to digital converter, and it will give me a 16-bit value back. And this is actually buffered slightly either side of the +5 volt supply. So it will sample just above it, and it will sample just below 0 volts as well. That's I've chosen that because it gives me a definite 0 volt point. And I could put some, if I'm using very small signals, I could put a PGA in there, programmable gain amplifier, for example. What I've got then is a MUX, and I've got 8 pins input as well. So that gives me 8 analog pins that I can sample as I wish. Now, again, in firmware, I can change this so I can make this run constantly. So it could do, let's say, 20,000 samples per second. I could synchronize the MUX with it so that it would sequentially sample multiple inputs. And I can even connect a DMA to it so that it would, for example, each input could have, let's say, a 2K buffer and would constantly read 2,000 values into that buffer on an ongoing basis. There's all sorts of ways I can configure this. And in the designer, this is all just drag and drop. This is not a separate little diagram. This is actually the design in the design software. So by placing these on here, it generates all the API code and configures the chip so that these become available. Here we've got the UART, so that's giving us our communication with the PC. I decided to put a pulse width modulator in there. I do need to do a little bit of configuration on there. I think there might be a bug in the software where it's calculating frequency and timing off the clock. But again, I can change this clock on the fly if I wish to. And we've got 2 pulse width modulators which are synchronized together. So they have the same period, but they can have different periods on and off from each other, but they will remain in sync. And this one here is just buffering a terminal conversion output. I don't want it to be used as an input by mistake. Over here I've got four 12-bit VDACs, and I should mention, by the way, on this ADC I could change that to 20 bits if I want. I just decided to make it 16 because the code that I was adapting for this just happens to be 16-bit, and it just means moving 16-bit values around in the software instead of 32 bits. Okay, so 4 VDACs, each set at 12 bits, so 4 analog outputs, and I'm just showing some capacitors here just to remind myself that I need to connect each of those outputs to a 10 nanofarad capacitor. That's just to remove any tiny dithering noise off the end of that. I've put an SPI in there and an I2C as well. Now, the reason I'm not actually going to program all of this in this program, or even actually really to get this thing live and running, the reason I place these is I think that's what I want. There are still, I think, 6 pins available for other things, should I choose to do so. But this is pretty much what I'm likely to use, I think. Now, placing all this means I can then run the software and it will generate a pinout for this. And the reason I do it like that is because I've got a mix of analog and digital, and some pins are more directly connected to analog buses inside the chips than others, and digital, etc., etc. And I want to separate my analog and digital in the internal architecture, so we don't have noise and crosstalk and all that sort of nasty stuff. And it can do it itself, far, far better than I can ever do it. So I put it in there, let it do that. Then I might swap, for example, it might put 2 analog pins in the wrong way round for my liking, so I can swap those round, and then I can lock the pins, and then that's that design fitted. Because you know, otherwise we're not really getting an optimal design. So putting all the stuff in that I think I might want, and then generating it. So I could put another I2C in there, for example. There's tons and tons. I could put a quadrature decoder in. I could do all sorts of stuff. But anyway, enough's enough for the time being. So next thing was to find a case. So I've looked at various spare cases and I've come up with this one. Just move that out of the way. So I think this was a clearance from Maplin or somewhere. So it's a fully plastic case, but it's sort of all right. Nothing wrong with it really. It's a instrument case. It doesn't have a tilt bail, unfortunately, underneath, which is a shame. But yeah, it's all right. It does the job, I reckon. I might at some point replace the plastic front with an aluminium one, but for the minute I'm just going with plastic. And I have taken my plastic front and I've just finished drilling it. So what I've decided to do is put a load of these 9s on it. So these two are going to be the I/O ports. These are male, so those are going to go like that. Then the ADC is an input, so we'll put a male on that as well, and that will be a 15 pin. So I'll use 8 pins for the actual values. So these are 9 pins, and that 8 pin port, so I'll use 8 pins for the values plus 1 for ground, just in case I need it. I don't need it in this instance, but there we go. This one then is the ADC, so 8 pins along the top will be for the value, the 7 pins at the bottom I'll just ground. I decided to bring the plus minus 5 volts out, just on some little red connectors. Move these some bits so we can see it easier. On some nice red connectors and black. Then we've got, what do we got then? We've got a large connector then, somewhere, which I've lost, there it is, which is female, so I can't mix them up, and that's for the SPI, I2C and pulse width modulation stuff. And then the DAC can come out on a 9-pin female since it's an output. Then I thought, well, actually what I could do with is I'll put a BNC in for the 4 digital to analog converter channels as well, 1 for each channel, and the first 4 ADC channels I'll put a BNC in for those as well, just so I've got alternatives for connecting things up. I wouldn't normally use a BNC for a test jig because you want to remove the ability to make mistakes. So for example, for testing these, although they're very simple, I will make a connector that goes in here and here. And as part of the test routine, those two will then plug in together, because don't forget this has got a female here, and we'll have this thing plugged in, and I will actually plug in the piece that I'm going to give to the customer, and I'll test it right the way through. So we'll have a D sub 9 going to a male and a D sub 9 going to a female RJ45. So those will just plug in. They can't plug in anywhere else. It's impossible to connect them into any other port. Then they're plugged together, and then we'll actually run a self-test on the device itself to test the connectivity through those test connectors. If that passes, then we can introduce the device to be tested. So yeah, so all I've got to do now is put it all together. So as we can see, I have laminated this already, so I'm going to get trimming this and assembling. So in terms of mounting this guy, I'm just going to mount this on this piece of strip board. So here's the bottom of the case. I'm going to mount this on this piece of strip board. That will fasten in there, and I'll put a little support pad under there, and then this will fasten on around about there. And that gives me room for later if I want to put things like operational amplifiers in to buffer the outputs, for example, or I want to put some additional power facilities, or the ADCs I want to make bipolar or something like that. Then I'll need some additional components on here, and this I'll just solder out to a long USB connection sticking out the back. But in the future I might want to put a power supply or something like that in there as well. So this gives me loads of room to do that. And literally I'll just pin through here onto this strip board. So this is copper strips on the back. Hopefully you can see that on the camera. And then I can put some connecting pins on here, and they can connect through onto the panel connectors. And all these panel connectors are actually IDC connectors on the back for ribbon connectors, so I can just clamp them too. It just reduces the amount of bloody individual wires being soldered. Still individual wires at this end because it's strip board, not a PCB, but you know, it all helps. All right, not the neatest job I've ever done, but I think we're there. All of our cables are connected up, loads of grounds by the million. And looking good. Okay, and now time for some operational tests. I'm bound to find some problems along the way. I expect firmware problems, software problems, as well as a few hardware errors. At the moment I haven't got anything plugged into this at all. I've literally just got the unit plugged in to my laptop, and I've run up the software that I've written, the test scripts, and it happens to have test scripts loaded for US2000 to 2000C adapter, which obviously is what I'm ultimately working with now. Test fixture, this is the first test that I can run, and we can see that it's failed, but I don't really care about that. So we've started running it, and we can see the first test here. Start test 1, test SCPI connection, test SCPI connection connected, make or repair automated test unit firmware 1 revision 0. And that is my unit. Excellent news. So now it actually wants me to connect the DBA Ethernet cables end to end. So it's going to do a basic test on the setup of the two connectors which are intended to plug into these two ports. And of course they're not here, so this is going to fail. I'm expecting this to fail. So plug the male and female connector together. Well, okay, I haven't got the female and male connector, so we just click OK. And it's doing its test at the moment. So this has been set to stop on error, so it's going to do its first test, which is the end-to-end test. So it's done the first test, which it passed, which is double check and make sure I've got the unit connected. That's absolutely fine. And then test 2 is to test the DB8 and Ethernet cables end to end. So its output pattern 0, 0, 0, 0, loads of zeros, a 1, and it's received nothing on B. And the same with each pin in its respective connection. Now I wonder, so I have to have here an 8-pin female to 8-pin female, which hopefully isn't it first? Let's run the test fixture again. Put them together, please. Now let's run those tests. I do need to do a little bit of an update on here. That's indicating we do have a couple of problems. So I don't think that this has got any cross connections on it. It doesn't look like something that it should do. But maybe I'm wrong. And of course, maybe there's a cross connection inside the unit itself. But testing the cables end to end, its output pattern, it's turned on pin 2 and it's received pin 2 and 3. It's then turned on pin 3 and it's received pin 2 and 3 again. So it would actually indicate that there is a short circuit between 2 and 3. We kind of think that might be the case. Let's have the beepy thing running. Let's unplug it. And I don't know which is pin 2 and 3 on this, to be perfectly honest, but anyway. Ah, and look at that. This cable has a fault between the two pins specified. Now this isn't actually working with the numbering of the DB9 connector. It's going 1, 2, 3, 4, 5, 6, 7, 8. But there it is, we've got a 1.0 ohm short circuit between pins 2 and 3 on this. Amazing. So, funnily enough, it actually did its job. So let's run up putty and just take a quick look. So I want the, oh, I haven't got it. So I want COM9, I think it is. So the reason it works at 19200 baud is because that is actually the most reliable when you're deriving, because I'm deriving my timing for my UART on chip. I don't have exactly the right device speed to do that spot on. So yeah, 9200, I'll just choose terminal. I want an implicit line with one of those, and I want to be able to do local echo and force on, because otherwise it's a pain in the bum to use. We'll save this, not as that, we'll save this as, what is this, test unit. Okay, now we'll open that and we'll just type in start IDN, question mark, and there we go, we've got connection through into the device. So let me just see if I can, so digital system value A, comma 1. Okay, so if I probe on volts, channel A now, I should find nearly everything to be 0. I can get 0 very easy because I put it on there. So how about put a 1? So let's put this pin here to be 5 volts roughly. There it is, 4 point whatever. And that pin to be 0. Everything else would be close to 0. And it is, excellent. So if I now do dig colon val A comma 2, I would expect the pin 1 to now be off, which it is, and pin 2 to be on. There it is. So I can just continue on with my testing like this, putting each of the values out. Now let's have a look at port 0 on the DAC. DAC, is it DAC or VDAC? Val 0, comma 2.5. I've got to put my capacitors on, but even so I should still have something. Let's try the ADC with something. So let's plug in ADC port 0, turn on the power supply. So that should have about 4.13 volts or thereabouts. So if I do, let me just do star IDN question mark again, just make sure we're, try that again, star IDN question mark. Lovely, and then we'll do ADC :val question mark 0. 6641. That doesn't really help me, that's a count, not a value. Let's repeat it. ADC :val question mark 0. 2.54. Okay, now we're looking good. I think I was over volts there. So 2.54762. Let's actually find out what it is. On there. 2.517. And I've got 2.547. Not bad, considering there's no calibration on that at all. Let's just turn that down a few millivolts. ADC :val question mark base 0. That's not doing what I'm hoping for. Anyway, that's a bit of troubleshooting to do later, because I really need to make sure that these digital ports work so I can actually get my devices tested. Let's also just run a quick test on the voltage output here to make sure I've got a 5 volt out. Yeah, 4.9, thereabouts. Okay, so I've done a few little modifications to this. So one of them is on each of the digital output ports, which is a 9-pin D. I was using 8 of those for data and 1 for ground. And what I've done now is I've actually brought another port onto it. So port A, for example, has 8-pin port A, and it has a single bit that can be set and cleared as well on the 9th pin, and the same with this one here. So those are ports C and D. I've realised the reason that the DAC had the wrong pins is because the cable is reversed on it. So yeah, that's okay. I might just, since I'm going to be sticking a sticker on the top which shows where all the pins are going to be, which will be a bit kind of like, kind of look, I don't know if that shows on the camera, a bit like that. So that's going to go on top to show what connects to what. So I'm not going to bother to change that round. I have remembered though to put the 10 nanofarad capacitors on the digital to analog converter on there. So new stuff, I've added the ability to select multiple tests. So I'm just going to, we'll do no device test at the moment, and I'm going to make this a bit bigger. It's a bit small screen, I'll make it a bit bigger this way as well, just so we've got plenty of real estate. And yeah, we'll just test the fixture to begin with. Leave all ports disconnected. Okay. So there we can see that it actually now reports progress as it works. And these little stickers on the, or little indicators on the left hand side now sort of show the progress. They switch to running and then passed in this case. So so fixture test, no device connected, showing the start date and things, starting tests, testing the connection, and all it's doing is making sure that it gets this make or repair automated test unit firmware thing back again. And that passed. Let's test the device then, and we'll just run that with everything so we can see the progress is coming down here, and we can see some passes as it's reporting its sort of progress. Now I haven't got stop on error working here, so just going to scroll up here. I should make this auto scroll I suppose as well, and there we go, we've passed. So what it's done basically is it's done that little test again just to make sure its comms is working, and then it's gone through and it has output a value onto the various ports and read those values back. So it's actually testing port A and B and just verifying that the value it outputs is what it reads back. If there's a short circuit, then the value that it reads back will be different. Okay, so let's instead switch the US2000 to US2000C because that's what I actually want to test. And click on test fixture. Connect the test unit and DB9 adapters in the ports. Okay. Yeah. Okay, I've done that. So it's run the first test. I'll just move this out of the way. You can see that it's now got a status of running on the left hand side. Oops, let me switch screen. It's got a status of running on the left hand side. It's run the first test, and let me move that out of the way. And we can see that so far it's reported test 1, test the Scuppy connection. Yeah, it got the right ID back. And now it's ready to start test 2, which is just going to test these cables end to end. So it wants me to plug them together. Comme ça. And click OK. Okay, and we can see the pass results coming out as we go. So it's literally just checking here that the end-to-end connection is valid. There we go. Yeah, and then it's doing a short circuit test on both cables. Brilliant. Okay, so let's see it fail for a minute. So I won't bother to actually put the real adapter in this. I'll just run the test without it. So click on test device. Oh, hang on a minute. Let's switch back again. So here's our pass on the test fixture. So we know that our wires that we're going to be using to do our tests are actually working. So here's our end-to-end. So it's pushing values through from one end to the other and checking that there is no like crossed wires or anything like that in there. Then it's testing each port for shorts, both ends, because it's going to need to do that test when we actually do the real test proper. Okay, so at the bottom at the moment I've got the test results still from when I did the simple nothing connected test. Now I'm going to force this to fault because I'm going to run this test now, the device test, but I'm not actually going to put the adapter in it. I've just got my straight through connection still. So this should prove that we see errors. So connect the adapter port A to the USB 2000B end and insert a short Ethernet cable into US2C and port B. But I'm not going to do that. I'm going to have a faulty adapter, so to speak. So here we go. End-to-end mapping. Errors. Bugger. Just what we are expecting, really. So it output, first error here, it output to the US2000 a 1 on pin 1. It expected to get nothing back at all. It expected 0, but it actually got a 1, which is pin 1 is on the right hand side. Error, mapping, pin 2. It expected 6 to be shown up because that's the actual weird and wonderful mapping that's going on inside the adapter. And it actually got pin 2, so it didn't like that either. When it got to pins 4 and 5, they passed because they are actually supposed to be straight through connections. So, okay, so a whole bunch of failures on that, and then it runs its short circuit tests. And then finally at the bottom it gives us a summary. It says, look, I passed one test, which was the short circuit test, but I didn't pass the other test. Okay, let's put an actual adapter in then. So here is one fully constructed adapter, complete with label and everything. And this is essentially how I supply them, which is with this cable already plugged in, ready to go, so that people don't get them the wrong way around, I hope. So let's plug this guy in. And click on the test device button. Okay, we are done. Okay, and let's see, hopefully, that we get a lot of passes. So there you go, pass, 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 pass. More passes. Cool, we've passed. Fantastic. Now, one of the useful things that we can do with this, I haven't actually put it in yet. I need to put a little, up at the top here I'm going to put a little thing that will allow you to put a serial number in and things like that. And then that will be put into the test report, which is this bottom panel. So there is space for a serial. I've already coded for a serial number, but I just haven't provided the box to put it in yet. And it will insert it in its top line of the test report. But we can do file print and actually print the contents of this bottom panel will actually print out. So there we go, one completed auto test system. And as I described, I have actually gone about making that a very, very versatile and general purpose system. So some of the other tests that I've programmed in already: Ethernet direct connection, so I'm test an Ethernet cable. Now I do have an Ethernet cable tester, but you know, this will be pretty good. And a deep, because this will clearly indicate what it's doing. It will check for all sorts of stuff. DB9 non-modem cable, because I've had a few faults on those over time, and there'll be a couple of other types of modem cable that I'll want to test as well, serial cables. And of course we've still got the ADC and the DAC and pulse width modulations and stuff like that. So we'll be able to do things like testing servos and all sorts of bits and pieces. Anyway, right, there we have it. Success. I did intend to include some explanation about the firmware code and the Java code, but things just became too long. Anyway, I hope you have enjoyed what I have put in this video. If you did, don't forget to like and subscribe. See you next time. Bye for now.